This video is about the action potential, a particular kind of signal that occurs in many neurons in the brain. You'll get a chance to apply what you learned about how the resting membrane potential comes about to make some educated guesses about how action potentials occur as we go along. So recall that the resting membrane potential is created by a combination of a concentration gradient in which there is more potassium inside the neuron and more sodium outside, and a leaky membrane that lets potassium flow outward. This leakage creates an electrical gradient of about -70 millivolts. But anything that alters this process will have the effect of changing that electrical potential. And here's a graph of what happens in many neurons. The voltage of the neuron might be sitting right about here at -70 millivolts. But then there is a sharp deflection in activity. The voltage suddenly goes way more positive and then comes back down again. That spike in voltage is an action potential, and many of us just refer to them as spikes. I'll use the terms spike and action potential interchangeably throughout this class. You already know why the voltage sits down here at about -70 millivolts, but what makes it go up again? And what makes it come back down? Both parts involve the same principles that we talked about last time, but with some new design features in the form of additional ion channels. Let's start with the rising phase of the spike or action potential, and this is caused by the opening of sodium channels. Now, based on what you learned in the last video, you should be able to make some predictions about what will happen when the sodium channels open. Well, when sodium channels are open, sodium starts to pour into the neuron. The potassium channels are still here, but now there are some new sodium channels in this diagram, and the sodium can enter the neuron through those channels. Well, what do you think that's going to do? What effect do you think this sodium influx will have on the neuron's membrane potential? The sodium influx makes the membrane potential more positive. Initially, it's just simply a little bit more positive than it was before, but is still actually negative. But eventually it becomes actually positive, crossing the zero voltage and becoming a truly positive membrane potential. And that involves a positive feedback loop. The membrane contains sodium channels that are voltage sensitive. As the membrane potential becomes more positive, more of these channels start to open, and that allows sodium to flow in. That continued influx of sodium causes the membrane potential to become still more positive. So it goes up and up and up until it approaches about +40 millivolts. At about that point, something else starts to happen. As you can see, the membrane potential starts to come back down again. Can you guess why? So the descending side of the spike is due to several factors. It's due to an activation of voltage-sensitive sodium channels. That means that not only are they closed, but they can't be reopened right away. They can't actually reopen until the membrane returns to rest. That prevents these channels from reopening prematurely as the voltage starts to drop. The second factor is that there are also voltage-sensitive potassium channels. These open up, increasing potassium's contribution to the membrane potential and restoring the resting membrane potential. One thing I glossed over is what starts the process to begin with. Action potentials can actually be triggered by two different kinds of events depending on the type of neuron. Sometimes the neuron is a sensory receptor. In that case, it is a physical stimulus that sets in motion the process that triggers an action potential. In other cases, the neuron receives input from other neurons via a synapse, and we'll talk more about this process in a later video. One last important point to note about action potentials. Once they are triggered, they are all pretty much alike. That is, this spike is pretty much the same shape as this spike, and so forth. And that means that information is contained in the rate or timing of action potentials, but not so much in the features like their size or shape. So we'll generally ignore the size and shape of action potentials and just talk about neural activity in terms of how many action potentials are occurring in a period of time. So now I hope that you have an intuitive understanding of how this magical electrical activity in neurons actually arises. And now we're ready to return to body position sensing and talk about how the body position sensor neurons detect and report body position.